Hey everyone, welcome back. Today we're diving into a topic that's getting a lot of attention in the local AI community right now. The new generation of mixture of experts models that can actually run on your own computer. We're comparing three of the most exciting ones: GLM-4.7 Flash from Zhihu AI, Qwen 3.6 from Alibaba Cloud, and Gemma 4 from Google DeepMind. All three were released around April 2026, and all three can run locally on consumer hardware. Let's break down what makes each one tick, what the benchmarks say, and most importantly, which one is right for you. Something really remarkable has happened in AI over the last couple of years. Frontier-level AI performance, the kind you used to only get from cloud APIs, can now run entirely on a gaming PC in your bedroom. That's not an exaggeration. These three models each pack 25 to 35 billion parameters total, yet only activate 3 to 4 billion of those parameters when answering any given question. That's the magic of the mixture of experts architecture. You get the knowledge base of a massive model at the compute cost of a much smaller one. Let's start with the architectural foundations, because understanding how these models are built explains almost everything about their strengths and weaknesses. All three use the MoE approach, mixture of experts, but they take very different paths in how they implement it. Think of MoE like a company with hundreds of specialized teams. When a task comes in, only the most relevant teams are activated, rather than the entire workforce. Here's the quick overview. GLM-4.7 Flash has 30 billion total parameters, activates about 3 to 3.6 billion, and supports a 128K context window extendable to 200K. It's text-only and laser-focused on speed and agent coding. Qwen 3.6 A3B has the largest footprint at 35 billion parameters, activates just 3 billion, and supports up to a 1 million token context window. It handles both text and vision. Gemma 4.26 A4B has 25.2 billion total parameters, activates 3.8 billion, and supports a 256K context window. It's the most versatile, handling text, vision, and even video up to 60 seconds. GLM-4.7 Flash's biggest architectural trick is speculative decoding. It uses a combination of multi-token prediction and the Eagle algorithm to dramatically reduce the time it takes to generate each token. In practice, this means you get latency of around 2 seconds for the first token, and a throughput of over 50 tokens per second. For an agent that's calling tools and running code in a loop, that speed difference is enormous. It's also MIT licensed, which means you can use it commercially without any restrictions. Qwen 3.6 is architecturally the most complex of the three. It uses a hybrid attention pattern that alternates between gated delta net, a form of linear attention, and standard gated attention, combined with MoE blocks. This design lowers computational complexity in long contexts while preventing information loss. It uses 256 total experts, activating 8 routed experts plus 1 shared expert per token. Essentially, it distills the reasoning power of the much larger Qwen 3235B model down into a 35B frame. Gemma 4 uses sliding window attention (SWA), which only attends to the nearest 1024 tokens at each layer. This keeps memory usage from exploding even when processing a 256K context. It also has a vision encoder that supports variable aspect ratios, meaning it doesn't distort or resize your images before processing them. And it natively handles video at up to 60 seconds and 1 frame per second, something neither of the other two models can do. Now let's talk about VRAM requirements. We're focusing on the Q4KM 4-bit quantization format, the most popular choice in the local AI community, because it keeps hardware costs realistic while preserving most performance. Each model lands in a different VRAM tier, which is one of the most important practical factors in deciding which one to run. Gemma 4 is the most accessible. At 4-bit, its weight's compressed to about 14 to 15.4 gigabytes, fitting on a 16 gigabytes VRAM card like an RTX 4080 or RTX 4070 Ti Super. However, you need to manage the SWA cache carefully. By default, multiple parallel slots cause VRAM to spike. Using the -NP1 flag in llama.cpp drops the SWA cache from 900 megabytes down to 300 megabytes. You can also offload the vision module to system RAM with the no-mm-proj offload flag, freeing up even more headroom. Qwen 3.6 needs more GPU power. Even at 4-bit, the 35 billion parameter count means weights take up around 21.5 gigabytes or more. That's too much for a 16 gigabytes card. Mixing GPU and CPU memory causes severe speed penalties, so you really need a 24 gigabytes VRAM card, like an RTX 3090 or RTX 4090. In that setup, you can compress the KV cache to fit a 150K context window within 24 gigabytes. GLM-4.7 flash also targets the 24 gigabytes VRAM tier. At 4-bit, the 30 billion parameters compress to about 18 to 19 gigabytes, fitting comfortably on a single 24 gigabytes GPU with room for KV cache. Combined with speculative decoding, this gives it excellent practical throughput. Community tests confirm it runs the full agent workflow without bottlenecks on an RTX 3090 or 4090. Now it's time to look at benchmarks, the numbers that tell us how these models actually perform. We'll walk through 3 categories: coding and agent capabilities, mathematical reasoning, and multimodal performance. These benchmarks aren't perfect, but together they give us a strong picture of where each model excels and where it falls short. Starting with coding and agent capabilities, the area most people care about. For SWE Bench Verified, which tests autonomous bug fixing on real GitHub repositories, GLM-4.7 Flash scored 59.2%. Qwen 3.6 scored 67.2% on SWE Bench Multilingual. Gemma 4 led on Tau Squared Bench for agentic tool interaction with 85.5%. On Live Code Bench V6 for competitive programming, Qwen 3.6 topped out at 80.4%. Gemma 4 followed at 77.1%. And GLM-4.7 Flash scored 64%. For math and reasoning, GLM-4.7 Flash scored 91.6% on MoE 2025, a remarkable result. Gemma 4 scored 88.3% on MoE 2026. On humanities last exam, Qwen 3.6 led with 21.4%, GLM-4.7 Flash scored 14.4%, and Gemma 4 scored 8.7%. On GPQA Diamond for scientific knowledge, Qwen 3.6 scored 86%, Gemma 4 scored 82.3%, and GLM-4.7 Flash scored 75.2%. For multimodal capabilities, GLM-4.7 Flash is text-only. Gemma 4 scores 73.8% on MMMU Pro and 86.3% on MMMLU. Its variable aspect ratio encoder processes images without distortion. Qwen 3.6 achieves 85.2% on MMLU Pro and excels at visual business tasks like analyzing front-end UIs. Both are strong multimodal engines optimized for slightly different workflows. Numbers only tell part of the story. Let's look at what real users actually experienced when they deployed these 3 models in live development environments. We'll go through each model one by one and see what patterns emerged that the benchmarks simply can't capture. Gemma 4 is fast and concise as an agent. It gets to the point quickly, uses fewer tokens per turn, and feels highly responsive. It particularly shines at front-end UI generation, with complex design prompts involving Tailwind CSS and intricate layouts, following instructional structure closely and producing aesthetically polished results. Qwen 3.6 does something counterintuitive. It generates extremely long thinking traces before producing an answer. At first glance, this seems wasteful, but in an autonomous coding workflow, those verbose traces act as insurance. By mapping out every logical branch before committing to a solution, Qwen 3.6 produces near-perfect code on the first try, completing complex Python debugging tasks in significantly fewer agent turns than faster but less thorough models. GLM-4.7 Flash integrates cleanly with agent tooling and performs reliably in web UI and terminal environments. Users found it highly consistent for tool calling, code execution, and multi-agent call chains. Temperature 1.0 with top-P 0.95 for general use and temperature 0.7 for tool calling gives the best results. Its lightweight footprint keeps it fast, even under the repetitive call patterns of agentic workflows. Here's an insight that reframes Qwen 3.6's verbose reasoning. In a chat interface, generating thousands of tokens before answering feels like waste. But in an autonomous agent loop, where the model writes code, runs tests, and fixes bugs over multiple turns, that verbosity functions as cognitive insurance. A faster model might respond in 10 seconds per turn, but take 6 rounds to arrive at working code. Qwen 3.6 might take 60 seconds for the first response, but works through edge cases internally and reaches correct, deployable code in 1 or 2 turns. When you measure total loop time rather than single-turn latency, Qwen 3.6 is often the more efficient choice. The 4-bit Q4KM format has democratized access to powerful AI, but it introduces a subtle trade-off. While 4-bit quantization barely affects text generation or summarization quality, it does increase the probability of micro-hallucinations in coding tasks. Small errors like missing parentheses, wrong file paths, or incorrect function signatures. Even the best models here aren't immune. The community has implicitly accepted this compromise. Smooth local performance in exchange for the occasional minor error. The path forward likely requires mixed precision quantization, keeping the layers most responsible for precise tool calling at higher bit depth while compressing less critical layers further. Gemma 4's SWA architecture and the intense VRAM optimization it required point to a shift in how we should think about local AI infrastructure. The challenge is no longer just fitting weights into memory. It's about managing dynamic memory state during inference, controlling how the KV cache and attention windows grow as context accumulates. If you run Gemma 4 with 4 parallel processing slots under default settings, the SWA cache overwhelms a 16 GB system, even though the weights only use 14 GB. The discovery of the -NP1 flag and vision module offloading shows that the real bottleneck has shifted from model size to inference memory management. The next wave of local AI progress will be smarter runtime memory allocation, not just smaller models. So let's bring it together. These 3 models are the best of local AI in 2026, but they serve different needs. If you have a 16 GB VRAM GPU and want a fast, multimodal agent for coding, translation, and UI generation, Gemma 4.6b is your answer, as long as you configure the SWA memory flags correctly. If you have a 24 GB GPU and your priority is complex autonomous coding with deep reasoning and minimal turn count, Qwen 3.635b is the most reliable choice. And if you want a fast, commercially free, text-first coding agent on a 24 GB GPU GLM-4.7, Flash delivers speed, consistency, and tool calling reliability that's hard to beat. That's it for today. See you in the next one.